This is Unit 3, Video 11. In this video, we will talk about intermolecular forces. They're also known as van der Waals forces, named after Mr. van der Waal, who first described them. Now, these are the forces of attraction between molecules. So here you have two molecules. Both of them are actually hydrochloric acid, HCl. And notice this dashed line is representing the force of attraction between these two molecules. These two molecules actually attract one another. Now, this is not to be confused with intramolecular force. An intramolecular force is the force of attraction within a molecule, what keeps the molecule together. And this is a strong bond. This is a covalent bond. So in fact, intermolecular forces, these forces here, influence the physical properties of a substance. And if you want to break them, you just undergo a physical change. Whereas the intramolecular forces, this requires a chemical change to break. So these are much stronger. And we've actually discussed intramolecular bonds earlier in the chapter. Here we're going to focus on these intermolecular forces. Here we go. Maybe. Oh. Try again. Here we are. So the intermolecular forces will determine the physical properties of a substance, whether it's a gas, a liquid, or a solid. So if it's a gas, technically the intermolecular forces will be non-existent, as you'll see. Or you can say the weakest. In a liquid, the intermolecular forces are definitely there, keeping the molecules together, allowing them to flow. And in a solid, they are the strongest. That's why molecules can't really even move around. Now, these forces also influence things like viscosity, things like surface tension, volatility, heat capacity. A few of these we'll discuss in a future chapter. But the point is, these forces influence the physical properties and describe the behavior, the physical behavior of molecules. We're going to look at three of them. The first one will be, looks like there's a little bit of trouble here, no worries. Okay, the first one is something called London dispersion force. Now, focus on this word dispersion, because what happens, the electrons will be dispersed. And this is a temporary polarization of electron density due to the movement of the electrons. So what happens is you have here a nonpolar molecule. So here you have a nucleus, notice, and an electron cloud around it. Now, notice the electron cloud is centered off the nucleus. Now, this is because the electron cloud can move, the electrons can move around all over the atom, and momentarily they end up on the left side, momentarily they end up here. That's why that's a negative, and that's what the red represents. And then what happens is, if it comes close to another atom, the same thing happens to the other atom. So the positive, for example, induces the same thing in another atom, and essentially this electron cloud, you could say, pushes away these electrons to that side. And then you induce, or you create a temporary excess of electrons on this side, and then a temporary, you could say, lack of electrons on this side. And so that creates a temporary positive and negative charge. Now, this allows the molecules to actually have an attractive force between each other, and we call this the London dispersion force. So here it says, this is the tendency of electron clouds to distort. And polarizability is what we call this. So the more polarizable a molecule, usually the bigger the electron cloud that it has. And as you'll see, that means it has more electrons and usually a bigger molar mass. Okay, so here's two examples. So London dispersion forces actually exist between all atoms or molecules, but they are the only forces in nonpolar molecules. So nonpolar molecules are technically evenly distributed, and so there has to be some sort of force between the molecule, because those molecules, even nonpolar molecules, can become liquids and solids if you cool them far enough. And in general, their strength increases as the number of electrons in a molecule increase. So the more electrons you have, the more polarizable the cloud is, the electron cloud. And here it says, even though the forces are very weak, they actually contribute significantly to the attraction between large molecules. So if you have a very large molecule, it could still be a liquid or even a solid, and that would be explained by these dispersion forces. And large surface area is what helps them be strong. In fact, I think we'll take a look at a few molecules here just to explain that difference eventually. So the second one is dipole-dipole forces. Now, dipole-dipole force is the attraction between positive and negative dipoles in a polar molecule. So a polar molecule technically has permanent negative and permanent positive states, or you can say these are partial charges. And because it's polar, you have more electrons on this side of the molecule, you have less electrons on this side, that automatically attracts a neighboring molecule. So you can see the force of attraction between this negative and this positive down here, and same thing between this negative and this positive. So these molecules actually have attraction kind of built into them, and polar molecules, all polar molecules, will have dipole-dipole interactions. That's why it's called dipole, because it's referring to a polar molecule, a molecule that is permanently partially negative and partially positive, in contrast to the previous one, which is the temporary induction or inducing of the negative and positive. So here is an example between the two. Butane, which is this big molecule here, it's not very big, but you'll see that it's evenly distributed. It all looks evenly spread out. The formula for butane is C4H10. So you have 4 carbons and the hydrogens completely evenly spread out, and it is nonpolar. So London dispersion forces are the only ones that are present, and because that's a weak force, butane is a gas. In fact, it boils right around the melting point of water, about 0 degrees Celsius. Acetone, on the other hand, take a look at acetone. It is a polar molecule. It's a polar molecule because you have an oxygen with a lot of electron density up here, which creates a partial negative charge to the top of the molecule, and it being polar exhibits dipole-dipole interactions. And so acetone is a liquid. Its boiling point, notice, is quite a bit above room temperature. It's not difficult to boil, but it is a liquid nonetheless. So that's kind of the difference between them. These forces are reflected in the actual physical properties of these molecules. The third force then is something called hydrogen bonding. This is actually the strongest of the forces. So this is a force of attraction between the partial positive charge on a hydrogen bonded to an atom of high electronegativity. So we have 3 atoms that will be involved in hydrogen bonding. That's the fluorine, the oxygen, and nitrogen. And these are the 3 most electronegative elements. If you remember, the most electronegative elements exist up here. Electronegativity increases this way, and it's actually FON that we asked you to memorize as the most electronegative. Now the way this works is the electronegative element, like oxygen, is so strong at pulling electrons toward itself that it pulls the electron off the hydrogen very significantly. Most of the hydrogen doesn't have the electron. And the interesting thing about hydrogen, remember, hydrogen is the only element that contains only 1 electron. It only has 1 electron. So when you pull that electron off of it, you're actually exposing the nucleus. And that's why you create a very, very positive charge in the case of hydrogen. And only these 3 elements are able to pull the electron off of the hydrogen that significantly, you can say. Now when this happens, this charge becomes very positive. You get a very, very positive side here on the hydrogen, which then is attracted to the negative oxygen of a neighboring molecule. Remember, this right here is between the molecules. Here you have 2 molecules. Here's 1 water molecule. Here's another water molecule. And the force of attraction between the molecule is the intermolecular force. In this case, it's the hydrogen bond. And these are very strong. So here's another picture of it with the molecules themselves. And this is so strong that it actually changes the properties of these substances that have hydrogen bonding, like water. And you can think of hydrogen bonding as a very strong version of the dipole-dipole interaction. So technically water is just a polar molecule, but because it has an oxygen bonded to a hydrogen, that creates a very, very big difference. And it's just a very big difference compared to a regular polar molecule. So these are very important, as you'll see. Now, to show you the difference, the reason why scientists came up with a separate category just for hydrogen bonding instead of calling it very strong dipole-dipole is they compared similar molecules together. So if you compare the boiling points of water, the picture looks like this. So what we have here is we have the boiling points. Here's the boiling point on the y-axis for a bunch of different substances in the same column. In fact, what you do here is this red line here represents group 16 elements. That's oxygen, sulfur, selenium, and tellurium. So as you go down the group, as you go down group 16, you encounter these atoms. Now, if you bond each of them with hydrogen, and notice that they form the same formula, H2S, H2O, that's because similar reactivity based on Mendeleev's arrangement. But what you'll see is there's a nice, neat little pattern between sulfur, selenium, and tellurium. Notice they just increase in the boiling point, which is expected. However, water should be maybe somewhere down here. I mean, this is the graph that you would expect. If we do it in red just to extend it, that's the graph that you would expect for H2O. However, that is not the case. Water has an enormously high melting point and boiling point in this case. And so that must be explained. So because of this anomaly in the trend, we said that oxygen actually has a very, very strange effect on hydrogen bonding. And so that's why we came up with this third category of forces. Same exact thing with fluorine. If you do the same thing with fluorine, if you plot the halogen, hydrogen, halogen boiling points, you'll see that there's a nice progression, and you would expect maybe HF to do something like this, but no, HF is all the way up here. So we also have to explain the same trend, and we say that HF also has hydrogen bonding. So this hydrogen bonding business actually influences very strongly these molecules. So water, for example, has strange physical properties. For example, it has high surface tension. You can actually float metals if you do it right on water, and it exhibits a lower density in its solid state. So ice floats because of this. Because the molecules have such strong attractions to each other, they're able to arrange in a way that creates spaces between the molecules and expands. Alright, let's go ahead and do an example or two, and we'll be finished with the video. So tell which intermolecular forces are present between the molecules below. Now what you have to do is you have to draw the Lewis structure, and you have to find out whether it's polar or nonpolar. That's really the essence of this. So in the case of CF4, if we draw the Lewis structure, what you'll see is that you have 4 fluorines connected to the carbon, everyone with an octet. It should look like this. Now, the next step is to predict whether this molecule is polar or nonpolar. And this molecule, being evenly spread out, should be nonpolar. In fact, you get a tetrahedral arrangement of molecular geometry. Here it is, and all 4 of them, remember, go on opposite sides to create a nonpolar molecule. Now, because it's nonpolar, the only forces present in it are London dispersion forces. So we'll say London dispersion, and you can actually do just with L-D for London dispersion. You can shorthand it. Alright, so London dispersion in the case of CF4. In the case of pH3, if you draw the Lewis structure of pH3, you'll have a phosphorus, and you'll have 3 hydrogens, like so. And you should have a lone pair on the phosphorus. Now in this case, the molecule is polar. We know it's polar because it has trigonal pyramidal geometry, and that is asymmetric. So this is a polar molecule. Now, it being polar will exhibit dipole-dipole forces, and that's the whole idea. So here you have dipole-dipole forces for this molecule. Now, it turns out we said all molecules also have London dispersion forces, so this will also have London dispersion. All you need to have London dispersion are electrons. So every molecule that has electrons, and even atoms like argon that have electrons, will have London dispersion forces. And then the final one is NH3. Now NH3 looks very much like a pH3, except that actually it looks exactly like pH3. So you would expect the whole thing to also be polar for the same reason. So this is polar. And so you definitely expect it to be London dispersion. I'm sorry, to be a dipole-dipole, because it's polar. So it has dipole-dipole forces. Again, we said all molecules have London dispersion forces operating within them. And in this case, you have a very electronegative atom, nitrogen, on a hydrogen. So you actually have hydrogen bonding as well. And the more important force will be hydrogen bonding. So as you'll see, this is the strongest. This is second strongest, and London dispersion is the weakest, is the idea. Now, as we'll see, these forces range in strength. So for example, you can have really strong London dispersion forces if the molecule is big, and you can have weak dipole-dipole forces if it's not a very polar molecule. So polarity, there's a range in polarity, there's a range in London dispersion forces, and there's a range in hydrogen bonding. And we'll discuss those in the next lesson. All right, go ahead and try one on your own. Try this practice problem on your own, and this completes the video.